I completely
Yeah,
forgot.
no problem. No problem. Thank you for joining in anyway, because I do have another lesson very shortly after this one finishes. So I didn't want this one to overrun too much. So that's fine.
I understand, that's
It'll
fine.
be clear for the other lesson. Okay, good
Yeah.
stuff. So we said we want to focus on today looking at internal resistance and EMF, don't we?
Yes, we do.
Okay. So EMF and internal resistance. It's called internal res. Okay. So firstly, we know what this term means because we encountered it, and this stands for electromotive force.
That's scalar, isn't it?
Absolutely, it's a scalar quantity. So what do we mean by the electromotive force? What is it defined as? How would you define it?
Is it a force that pushes around the electricity?
Yeah, but you would not get a mark for that because then you are implying that electromotive force is actually a force. It is not a force. It's just the wrong word we use in physics, but we're not implying a force at all. Yeah. So what is electromotive force? Any ideas how to define it?
Is it the sum of all voltage in a circuit?
In a circuit. We're getting there. We're getting there. But remember, I'll remind you back to the basics of what happens in a circuit. So when electrons grab energy from the cell, they will transfer that energy to the bulb or the
Diodes.
component that consumes it. So across any component that consumes it, we have a PD, a potential difference. Yeah? So
Yep.
this is referring to energy being transferred from the electrons to the component. But energy is transferred from the cell to the electrons or the charge carriers. That we refer to as the EMF. And it is given the symbol E. So E is got the same formula as PD, but the way to think about it is E is energy transferred to charge carriers. Yeah, by the cell. Energy transferred to charge carriers from the cell divided by charge. Now, it's a good practice to write out formulas in terms of words, because then you can really know what is that term, what is it for. So I encourage that even to my year 13s, but I strongly encourage you to start thinking in terms of formulas of words. PD is the same as well. PD, they're both measured in volts. But PD now is equal to, it's given by the energy transferred from the charge carriers divided by charge. Okay, so all of them are the same really, but one is dealing with the energy transferred to the charge carriers, whereas PD is the energy transferred from the charge carriers. Do you understand that?
Yes, I do.
Excellent, right. So if we have to define EMF, sometimes the kind of questions that the examiner likes to ask is, they might ask a question like this. What is meant? How do you answer this question? What is meant by an EMF of 5 volts? How do you answer that? And this typically in your exam would be 2 marks.
Right, okay. Got 2 marks, 2 points. It means 5 volts of no. Is it the energy of the charge carried from the cell.
Yeah, and you're nearly there. But whenever you ask the question, Tom, and very, very keenly remember this, and there is a number, you need to use that number when talking about that definition.
Is it 5 volts of energy?
No, we don't say 5 volts of energy. So I'll just remind you what we mean. If we have 1 volt, this means 1 joule per coulomb of charge is passed between those 2 points. One joule per coulomb. If this was 2 volts, then it would be 2 joules per coulomb. If this was 3 volts, 3 joules per coulomb, because the volt is got the units joules. How much joules per 1 coulomb? That's what this unit is meaning here. Do you understand that?
Yes.
So what does 5 volts mean? It means that 5 joules is transferred per unit or per coulomb of charge. 5 joules is transferred per coulomb of charge that passes in the cell. Now I've used the definition, yeah? So 5 joules is transferred per coulomb of charge that passes through the cell. That is what an EMF of 5 volts means. If you're asked, what does a potential difference of 5 volts mean? Well, it strictly means that 5 joules of energy is transferred per coulomb of charge as it passes through that particular component that has 5 volts across it. Are you following so far?
Yes, sir.
Good, excellent. So now let's look at, so far what we've looked at is we have looked at blank page after current. We've looked at an ideal cell. An ideal cell simply has 2 terminals, a positive and a negative terminal. So this here is an ideal cell. But a real cell also has within it resistance. In other words, a real cell, an ideal cell is 100% efficient. It transfers all its energy to the charge carriers that pass through it. But a real cell is less than 100% efficient. Efficiency is less than 100%. Why? Because some of the energy which it could have transferred to the charge carriers is lost to what we call an internal resistance. So to represent this, we draw our cell like so. This here inside represents, so this is the internal resistance. So in other words, the energy that was available now will be lost to this internal resistance. Remember that whenever current flows through a resistor, what do we get? We get a heating effect. And when we have heat, we have dissipation. So we say, whenever current flows through a resistor, we have a heating effect. And we can calculate the amount of energy we lose as heat using the formula I squared R. This is also known as, this is also known as the Joule heating. We're going to be losing energy given by I squared R, where R is the value of the resistor. You following so far? Now this here simply is coming from P equals VI, but because we know that V equals IR, we take this IR and put it in place of the V, and we get I squared R. So if you want to work out the amount of energy that is lost in total, you'd have to multiply this by time, because as it is here, this just represents the power loss in a resistor. To find out the energy lost, you'd have to multiply that by time. Are you following? Because power is energy divided by time. So to find energy lost, it would be energy equals power times time. So if you knew the duration for which the current runs through a resistor, and you knew the current and you knew the resistance, you could work out how much energy has been dissipated. So here we say that this energy here, we have a heating effect. This dissipates. And what do I mean by dissipates energy?
Like spreads out into the environment.
Yeah, correct. This dissipates, or in other words, we have what is known as energy degradation. The energy is not as useful. We can't use it. It cannot be accessible to the rest of our circuit. So we call it energy degradation or dissipation of energy. Good. So that is the key thing I want you to understand. Now, the next thing we need to know is that internal resistance is a consequence of how a cell has to create energy. So there is no cell, no real cell that does not have an internal resistance. Every cell has an internal resistance because inside the cell is a chemical reaction, and no chemical reaction is 100% efficient. Are you okay with that?
Yeah.
Good. So let's go now and look at how the whole thing fits together from an energy balance point of view after current. So if I have a circuit like so, and I have my internal resistance, and I have my EMF denoted as E, and I have my internal resistance denoted by small r, and I have, just for argument's sake, I have another resistor here, which is my load. So this here now is the battery. This is the inside, sorry, of my cell, okay? And this is an external load given the symbol R. There will be a current flowing through this circuit. I am going to get a potential drop. In other words, I'm going to get energy lost through this big resistor, but I'm also going to get energy lost internally. So energy will be lost internally. In cell due to this. So if there's a current I, remember we can use Kirchhoff's second law. So using Kirchhoff's second law. Now what does Kirchhoff's second law state?
I don't actually know.
No problem.
I don't think I was in that lesson.
So the sum of the drops of the PD in a closed loop is always equal to the EMF. Now this here is as a consequence of what? Consequence of energy conservation. This is just conservation of energy because EMF is the energy available per coulomb. So we're dealing with energy here. So this here is simply conservation of energy applied. So what is the potential drop across this R? What can you say that potential drop is? If there's I and it's given R, what would it be?
Big I times big R.
Very good, excellent, well done, Tom. So this here, the potential there would be given by big I times big R. Very good. And what would the potential be across this internal resistance, the small one?
I times small
I times small r, good. Now these potential difference drops must equal the EMF. So I can rewrite this and say that E is equal to IR plus IR. And we can rewrite this and say, we can take the I out and write R plus R. Are you okay with that? So this is our first formula that can come in handy when we're doing calculations involving internal resistance and EMF. Let's look at this a little bit and expound on what this all means a little bit in different in a different, slightly different language. Okay, so let's just put blank page after current. If I have, again, there's my real cell or non-ideal cell, and I connect a voltmeter like so. And here I'll have a switch. And I have an external resistor as before. Just call this, sorry, R, and we're going to call this little R, and that's my EMF, and like so. So the first expression we have come up with first, if I've got, well, there'll be no current passing through here. So the first expression we got is EMF equals to I R plus IR. I've written it in this expanded form. These here, this term IR, we refer to it as the lost volts because it's lost inside the cell and it's not accessible to the outside cell. So it lost in cell, oops, lost inside cell. Are you following so far?
Yes, sir.
So what would be available in terms of energy to this resistor would be given by the term E minus IR. This gives us available volts to R, to the external resistor. Now, these available volts that are available after you've lost some energy inside the cell, we have a term for these available volts. We call this here the terminal PD. Why is it called the terminal PD? Because if this switch is closed and you have a current, by the way, you need a current to get lost volts. So let's just remember, we can see that I times R. If I is 0, there are no lost volts. Please note. So we're going to state, and it's very important to remember, I can't emphasize it highly. So lost volts only happen when a current flows.
Yeah, but that's pretty standard. You have to times the current by resistance, and it would be 0 if the current was 0.
You're absolutely right. Okay, you're absolutely spot on. So we can rewrite this terminal PD, okay, is symbolized with the letter V, because it is the PD that you will measure on your voltmeter when there's a current flowing. That's why we call it the terminal PD. It is measured between the terminals of the battery. And we're only going to have a terminal PD, so to speak, when there is, so to speak, if you like, no current per se. But let's delve into this a little bit more again. Blank page after current. So I redraw my circuit again very quickly. And I have again my external resistor R, my small resistor that's E, and there we go. And let's just assume, oops, drew it too quick, I will put a switch in there as well. Okay, again. And I'll have my voltmeter like so. I'll connect it there. Okay, so we can rewrite that equation we wrote and say E minus IR equals to V. What did I say the V stands for?
Available volts to the external resistors.
Yeah, and we call that terminal PD, because it's the PD between the terminals of your cell. So when you look at your cell, yeah, these two are the terminals. So the PD you would read, so we call it the terminal PD. So let's imagine in this case that I have a voltmeter and my circuit or my switch is open. What would the current now be in the circuit? 0. Do you agree?
Yeah, because nothing's flowing.
Good. So if this is 0, am I going to get any lost volts if there's no current?
No.
No lost volts. That means that the reading on my voltmeter is going to be equal to what?
0.
No, quite. So if this is 0,
oh,
terminal PD is always, remember what I said, it's what the voltmeter will read. So just look at this. If this is 0, my equation is now E minus 0 is equal to V. So what will the reading be on the voltmeter now?
It'd be equal to the EMF.
Very good. So when the circuit, when switch is open, reading on the voltmeter will be equal to the EMF, will be equal to the value of the EMF. So in other words, if you want to work out the EMF of a cell, all you need to do is grab your cell and take a voltmeter and connect. Do not put any resistor in this circuit. So now it looks like this setup. It's just a voltmeter between the two terminals. Can you see? It's the same as what I've drawn here. Are you okay with that?
Yeah.
Very good. So to find the EMF, make sure there is no external load connected. Now the next part, now that we know this, what about if we want to work out what the internal resistance is now? So let's just insert page after current. Let's look at how this relates to, say, if we wanted to obtain a graph. So we know that E minus IR equals to V. It's a key point. So if I was to plot a graph, let's just say we wanted to plot a graph of terminal PD, V, which is in volts, against current. Now, how can I vary the current in a circuit? Well, if I wanted to vary the current in the circuit, my circuit would have to look like this, wouldn't it? That's my resistor R, that's my EMF. And over here, I would need to use a variable resistor. And of course, I will connect then my external voltmeter, which will give me my PD. Now, what will the graph look like as I vary the current? How will the graph look like? Well, to know that, I need to map this onto y equals mx plus c. How good are you at doing that, Tom?
I'm okay at it, not the best.
Okay, so can you tell me then how you would map this onto y equals mx plus c, what your gradient would represent, and roughly maybe what the shape might look like?
Well, I'd switch it the other way around, so it's v equals EMF
Yeah, so
minus
I write that as V equals E minus IR. Go on.
So I'm trying to set it up myself so I can help
Yeah,
myself.
go for it. Set it up yourself.
I'll probably switch it so it's V equals minus IR plus EMF, and then
Good. Okay. V equals minus IR plus E. Good.
so then the current is the gradient, the resistance. Sorry, current is the gradient, the resistance is X, and the EMF is the Y-intercept.
Not quite, but you well done for trying. So on the Y-axis, I've got V. So this is my there. What do I have on my X-axis? Go to your graph. What do I have on my X-axis?
You have current.
Current. Good. So on my X-axis is current. So you join these. Are you following? You need to absolutely master this skill. I can't emphasize it enough. And you need to be disciplined when you are circling or mapping them. So go to your X-axis, see what's there, and you will map that next to the X. Go to your Y-axis, see what's there, you will map that to your Y. Following so far? Yes. This means that the gradient will be given by what quantity?
B resistance, internal resistance.
Not quite. Look, no. There's a minus. We can't throw it away. There's a minus in front of, because this is not minus I. If this was minus I, then I would have circled minus I, but it's only just I. So what should the M represent?
EMF.
The M, just one moment, yeah? I've just got a knock on my door. I won't be too long at all. Just one moment, sorry. Where are we here? Sorry for that. Somebody was trying to sell me guide dogs or something like that. Right. Where are we at, Tom? Yes. So if we map it, there's still the minus. So don't forget that minus, okay? Don't forget any signs in front. Can you hear me okay, Tom?
I can hear you okay, yeah.
Great, okay. So there's a minus R, so the gradient is minus R. What does a negative gradient look like? Does it look like a line that goes this way or that way? A or B? Down, B. Correct. So this now already tells you that this thing is going to be going down.
Yeah.
You following?
Yeah. I just go grab a whiteboard pen quick, so this one's run out.
Of course, yeah, certainly.
I'll be 20 seconds. Right, got it.
Good.
Carry on. B is negative.
What is negative, sorry?
B would be a negative gradient.
Oh, the gradient, yes. The gradient is a negative gradient, correct. Not V, but minus R. Yeah?
Yeah.
So I may have heard you wrong. So minus R equals the gradient. What is the intercept going to be?
EMF.
Correct. Okay. So I can work out the intercept. There we go. And the gradient is my minus R. Spot on. Now that we've established this, typical questions are, why that as the current increases, the terminal PD decreases? Why?
Okay.
Remember again, hint, V is the terminal PD. Why as the current increases, does the terminal PD decrease? And this is what we're plotting on this side. This V here is the terminal PD.
it's because in the equation V equals E minus IR, as current increases, there's more to take away from E. So then the terminal PD would be less.
You're right. And I would be specific. I would say as the current increases, the number of lost volts, that's a term you want to use, increases. Yeah. Good. The lost volts increase, leaving a smaller value of the terminal PD, because there's more you're taking away from the EMF. Okay? Are we okay with that?
Yes, sir.
Excellent. Now, let's move on to another idea here, which is to do with power dissipated when you have got a non-ideal cell. So if this is R, that's little r, and that's E, and you've got a current flowing I, in terms of power, yesterday we looked at an equation for power. Well, what is the power that this cell is generating? What do you say in terms of the symbols that are on this board? What is the power generated by the cell?
Power equals I squared R.
Power. Well, you can't use I squared R. Now that power is for power dissipated. I'll almost use that word. So that's normally if current is moving in a resistor. So you ask yourself, what current is flowing through the resistor and what's the value of the resistance? That's the power, or that's the rate at which energy is being lost in that resistor. But what other expressions can we use here in terms of the power generated by the cell? Remember, we looked at our formula P equals VI.
Yeah.
This is the most important one to remember, because everything comes from this. P equals I squared R comes from this. P equals V squared over R comes from this. So this is very important to remember. I know it's in your data sheet, but it's worth remembering. Serve yourself a few seconds flicking through the pages. P equals VI. So the power generated by the cell would be the potential difference, E, times the current that is passing through the cell. So this will be given by E times I. What about the power dissipated in this big resistor? Now I can use that formula, I squared times R, because I've got an R and I know what the value of I is. So this here will be power dissipated in external resistor. What about the power dissipated in the internal resistor? What's that going to be?
Also be I squared R.
Yeah, correct. Small r. And this here is the power dissipated in internal resistor. So far, so good. So therefore, EI, so energy conservation, means that EI, the power generated inside, must be equal to I squared R plus I squared R. Remember this formula. Well, this here is the EMF. We're okay with that?
Yeah.
Good. If we had to plot, so if we had a variable resistor here, just to make life a little bit exciting, insert page, blank page after current. There we go. So that's little r, E, and this here is a variable resistor. And we try to plot a graph looking at, so this here, by the way, is what my external resistor is also sometimes known as your load. aka load. Okay, so if I wanted to look at or plot a graph of the power delivered in watts, and this is to the external load, power delivered to load.
Yep.
Yeah, against load resistance R. That's my load.
Yeah.
How will this vary as I change the value from 0 all the way to some maximum value of R? So this is a variable resistor, so it can go from 0 all the way to some maximum value of R. How will that change? Well, this would look something like this. When would maximum power be delivered to this load? Maximum power will be delivered when the value of the load resistance is the same as the value of the internal resistance. Now remember that little point, because they don't test it much, but it does come in and students forget because they don't do so many questions on this. So I can't highlight it enough. So please note, when the value of the external resistor is equal to the internal resistance, maximum power, max power is delivered to it. Ooh, is delivered to it. Now the it here, I mean the load, the external load is delivered to it, is delivered to it from the cell. We'll put this here so that we know it's not to be. Okay, so that's our graph there we're referring to. So load resistance, which would be of course in ohms, and your power delivered in watts. So when the value of that external load resistance, really I should label this load R, okay, because I've used the value R. Have you followed that so far?
Yeah.
Okay, now if you're doing A-level maths, I would have told you to differentiate this thing, do some calculus to prove to yourself that indeed, when the value of R equals to small r, only then do we get maximum power being delivered to the load. But you're not doing A-level maths, and they would never ask you in your exam to use any form of calculus to show that. So don't worry about that. Now, something else here just to touch on, okay? Very quickly and very briefly. If I have cells connected in parallel and each of them has an internal resistance, and let's imagine that we have an external load. And an EMF E. This here, this is the same as an equivalent circuit. I can replace all these three cells that are in parallel with one another and symbolize it with one cell that has still got a potential difference, sorry, an EMF of E. But this time around, what will the value of the internal resistance be? These three resistors. How can I find the equivalent resistor? Any ideas?
In parallel, so don't you do 1 over R plus 1 over R plus 1 over R equals?
Correct. 1 over R plus 1 over R plus 1 over R. Yeah. And what would that give me? So put R at the bottom. So I'd have 1 plus 1 plus 1. I would have 3 over R, but this is 1 over R total. So R total would be equal to what?
You just flip it, wouldn't you?
So to find the total resistance, you remember you have to find the reciprocal.
Would be minus R over 3.
No, it wouldn't be minus. It would just be R over 3. Why would it just be one R over 3?
I was
One
thinking the
plus-
negative reciprocal from perpendicular lines in maths.
No, sorry, there'll be no minusing here, Tom. So let's just think about it and just use some. This is, if you were given this question, it's like saying, make RT the subject of the formula. How would have you done this at GCSE? Meaning I want an equation that's going to say RT equals.
I would just flip it over because you can.
Sorry, is it just me? I think I've got my volume really low. Let me turn up my volume. I'm on 44%. No wonder I can hardly make up what you're saying. All right, maybe that might be better. Go on, Tom. Just say that again. I missed that part. I
would have flipped them all because it's 1 over, and then you can just flip them.
Yeah, absolutely. Just flip that RT over 1 because you flipped it that way. Flip it to R over 3. Or if you want to do it the long way, cross multiply. So you get R equals 3 RT, and then divide by 3, then divide by 3, and you have RT. Any of those are absolutely acceptable. So here now, we know that this would be equivalent to R over 3 with my external load, R. So just be mindful. What about if I had them in series?
In series, you add them together.
You add them together. So if I had a cell, R, E, and another one, this now would be the same as me. Sorry, that's E, that's R, that's E, that's R. Now we add the EMFs, they're in series. So the equivalent of this would be same as me drawing a cell with 3 times the EMF and 3 times the value of the internal resistance connected to a resistor R. Okay, so we can redraw this and draw it like that. Are you okay with that?
Yes.
Good, okay. By the way, so this here is what we call equivalent circuit. CCT means circuit for a parallel combination. This, on the other hand, now is an equivalent circuit for a series combination. Now, one last thing, and then we're going to go into some questions. Remember, if I have, I'm going back to an ideal cell here, and I have resistors R1 and I have resistors R2, and there is a potential difference of V1 across R1 and a potential difference of V2 across R2. Do you understand or appreciate that V1 over R1 must be equal to V2 over R2?
Yeah.
Good. This is so important because it will make a world of a difference when you start solving some of these problems in terms of internal resistance. How do you use this now? It's not really different to how it is arranged here. Only this time you have to think about breaking the circuit down a little bit, blank page after current. So if I redrew my, and I'll exaggerate it here, okay? E, little r, and big R, and this is still inside my circuit. If I connected a voltmeter, I know I can't, but if I connected a voltmeter inside and I had a value of VR, the voltage across R, and I also had another voltmeter, just like what I did, V big R.
Mm-hmm.
Do you agree that this circuit is no different to this? It's still a series circuit, only that one of the resistors is inside the cell. My R2 is inside the cell, and my R1 is the big R, which is on the outside. So this is no different to what I drew. Do you agree?
Yes.
Very good. I want you to appreciate that. Therefore, VR is going to represent the terminal PD in this case, because this stuff is inside.
Okay.
So VR over R is equal to, what's this VR going to represent now?
The internal, no, sorry.
Name, you know the name. Lost volts.
Yeah.
So VR over VR, little r over little r, which is the same as, we'll write this in words so it makes more, it's more alive for your brain to process. Terminal PD over external resistance value is equal to lost volts over internal resistance. If you can remember this, these formulas are not given in your textbook. These are just quick shortcuts of how to work with problems involving internal resistance.
More efficient as well.
Very efficiently, absolutely, because this is just, and like I say, you will not be given this formula, but if you can remember it, you've done yourself a big favor, Tom. Right.
Yeah.
We move on to doing some questions now. Oh, gosh, added pages on the wrong place. Sorry, I seem to have jumbled my pages. Oh dear. Anyway, it doesn't matter. Right, it's fine. It's fine. You've got the gist of it anyway. I'll try and see if I can jumble them. Right. Let's go for number one.
Okay, let's go.
Matter of fact, Tom. Yeah, well, it doesn't matter. Let's start off with number one. I wanted to start off with something where you could have applied directly what we've learned. So is it okay if I just halt you in your tracks? I do apologize.
Yeah, okay.
Because I'm just looking at the time. So I'll leave this one for you to do as homework. They're just some staples I want to make sure that we go through. Right, number two.
Okay. Mhm. This is a tricky one.
I'll give you a hint. Think back to the last concept I've just introduced to you. Think back to the last concept I just introduced to you, the easy way of thinking about it.
What the Kirchhoff's laws when adding them all together?
No. Even that one, I'm even going easier here. I'm going, where is it? I'm going here.
I think
You would do it, you can do it in your head without even needing a paper. If you go here, if you use the other formulas, you might then need a paper.
is the answer A.
Not quite. Shall I help you out with this one? Let's work through it.
I really don't know.
It's fine, don't worry. We'll work through it together. So remember I said, lost votes over little r is equal to terminal PD, what the vote meter reads in simple words, over big R. This big R is that R.
Yeah.
Says, so the reading on the voltmeter, let's imagine when the switch is open, the reading on the voltmeter is a V. Then you close it. What will now what will be the reading on the voltmeter?
V over 2.
V over 2. This V over 2, the reading on the voltmeter, is the terminal PD.
Yeah.
So if this is the terminal PD, what are my lost votes? How many votes did I lose if I started off with V? Because V here is now representing the EMF, because the switch is open. So how many votes have I lost if my terminal PD is V over 2?
Half of your votes.
Exactly, thank you. So lost votes equals V minus V over 2, which is V over 2. I plug that into there. V over 2, which is my lost votes, over little r is equal to my terminal PD is V over 2 over big R, which is 2 ohms. So what should my little r be for these two things to be equal? What should little r be?
Would you times onto the other side? So it's R equals
No,
a
no,
half.
no, no. Okay, I think you're overcomplicating the problem. If this is V over 2, so let's look at this. The left-hand side has got that, sorry, and it's also
R
left-hand side has got this. There's a 2 at the bottom. What do I need to make this side to make it exactly equal as the other side?
R equals 2.
Thank you.
I did it in a weird way and had R equals 2, but I didn't think I'd done it right because I substituted in V equals 4 and
Yeah.
my result was R equals 2.
I see. But can you see how quick this was done?
Yeah.
Yeah. Okay. Time for one more before we're out of time, unfortunately. All right, number 4. Have I got number 4?
Is it 1.3 ohms?
Not quite for that one. No, not quite. Let's look at it together again. Not to worry. So if we come here, now there's a few things I want you to pay particular attention to. I mentioned them, but it's always good to hear things 3 or 4 times before sometimes they sink in. So if my circuit is open and I put a voltmeter across it, what am I measuring? What is
Terminal
it? Sorry?
PD. Terminal PD.
Not the terminal PD. So it's not connected, there's no current. What will the value on this V be when there's no current flowing in the circuit? Remember that a voltmeter has infinite resistance, so it will not let any current flow in it. So what value will this give me when the circuit is open? When I just take a battery, remember I drew you a little image, and I said, take a cell and you connect a voltmeter across it. What does this voltmeter read?
The internal voltage, the lost volts.
No, there'll be no lost volts because there's no current. Remember, E is equal to IR plus IR. Here, there's no external resistor, and the voltmeter has infinite resistance. What does infinite resistance mean? No current passes through it. So the value I'm going to get is the EMF. So this here is the EMF. Are you following?
Yeah.
Good. Next thing, this is the EMF. I then connect my switch. The volts drop. So of 1.5, I'm now going to use lost volts over little r is equal to terminal PD over big R. So what are my lost volts? My lost volts are 1.45 minus 1.26 over little r is equal to, what's my terminal PD? What's the reading on my voltmeter? 1.26 over 10. Now you can do this literally in 30 seconds. These multiple choice questions, you don't want to spend more than a minute and a half. Much easier to work with this. So are you appreciating this concept of lost volts? You absolutely need to appreciate the idea of lost volts and the fact that when the switch is open, a voltmeter gives you the EMF. Because if you know the EMF, and then you know what the new reading is when there's a current flowing, you can work out what the lost volts are. In other words, EMF minus terminal PD
1.5 ohms.
is equal to lost volts. So the answer would be D. Did you follow that?
Yes.
Okay, great stuff. Tom, I have to leave it there, I'm afraid. But you have a lot of questions here to keep you super busy. Okay, and all of these will put you through your paces. There's also a long structured question. Right. Regards the next lesson now, when would you like to have the next lesson?
I could do Saturday, Tuesday, Wednesday.
Okay.
I can do any day next week apart from Friday.
Okay. I can't do Saturday. I can't do Saturday. I can just about do Sunday. I've got some activities with my little ones. We're going go-karting and doing a few things that day. So I could just about squeeze you in on Sunday, but failing to squeeze you in on Sunday, I can make up for the lost time over the week.
I cannot do Sunday at all. I can do any day next week apart from Friday.
So shall we pencil in next lesson for Monday then?
Yes, okay.
Okay. And if you have any problems, of course, remember there's support tomorrow and such, so we can pick up pieces if you need to. Okay. But I strongly, strongly, strongly recommend you listen back to the video, rewind parts, because I've mentioned all the key nuggets that you need. So it might just be a case of re-listening again, pausing the video and going, hang on, what did he just say there? Right, I'm going to write that down. Yeah? So it might be a case of that, plus also going through these questions, and then let me know how you get on. But the answers are also attached, so you can mark them once you have completed it. Is that okay?
Yes, sir.
Right, brilliant. Now, next lesson, what do you want to go through? You want to go through some moments?
Yeah, moments, please. I've been doing lots of revision on particles and the photoelectric effects and stuff like that.
Good.
I'm really good with that. It's just moments and other stuff which I'm struggling at. I've been able to revise and be pretty confident with other pieces.
No problem. Okay, great stuff. How did you find that?
Well, obviously I found the topic difficult, but I'm
I know.
slowly getting there. I just need to keep
You're
practicing.
slowly getting there. I agree. You are making steady strides, which is important. Right. I shall see you probably at school, but if I don't and we miss each other, I'll definitely see you on Monday. Okay. And I will email you what time. It is going to be Monday. Oh dear, Monday's a bank holiday, isn't it?
Yeah.
Monday's a bank holiday.
As long as it's not too early in the morning, I'll be okay.
You'll be fine. I'm going to propose an evening start.
Okay, that sounds good.
6:30 p.m. Sorry for that.
6:30. Okay, that's good.
6:30 p.m. Super. Okie dokie. I shall leave you to your devices, Tom, and I shall see you next week, Monday, and we'll pick up pieces then. You have a lovely afternoon. We've got enough to keep you busy.
You too, sir.
Bless. All right. Cheers, Tom.
Thank you.
All right.
Goodbye.
Bye. Bye.